In Egyptian mythology, Anubis was the jackal-headed god of mummification. He was the god of the dead, and the escort of the newly deceased into renewal in the afterlife. Could the LHC's Anubis become a similar escort, resurrecting particles that would have previously passed beyond our analysis and observation, and finally allow us to reach the hallowed ground beyond the standard model? Over the past century, we have learned an incredible amount about how the universe works at the tiniest scales. Particle colliders have identified the fundamental building blocks of our universe and brought together 3 of the 4 fundamental forces in the elegance of the standard model. A framework that has predicted or explained the vast majority of observations in fundamental particle physics for the last half-century. However, we know that the standard model cannot be the final word. It cannot explain the existence of the dark matter that controls the rotational speed of distant galaxies. It does not address the fundamental force of gravity, and it cannot solve the conundrum of why our universe is dominated by matter rather than antimatter. It is a beautiful model, but we know it is incomplete. The burning question for particle physicists is, where are the cracks where new physics beyond the standard model might be hiding? Many physicists had hoped that the Large Hadron Collider, the world's largest and most powerful particle collider to date, would answer these questions in a flood of new, never-before-seen particles and interactions. However, despite the amazing discoveries of the LHC and the recent tantalizing hints of potential cracks in the standard model that have been generated by the LHC and the Fermilab Tevatron Collider, the standard model has remained impressively and frustratingly resilient. Last week, the LHC was powered up after a 3-year hiatus, during which the machine and its detectors were significantly upgraded. The LHC beams were fine-tuned and narrowed to increase the frequency of particle collisions, and detectors such as ATLAS, CMS, and LHCb were upgraded to deal with higher proton collision rates. The machine will produce as much data in the next 3 years as it did in the previous 10. The statistical chances of finding hints of new physics at the LHC are now potentially higher than they have ever been. However, the LHC has not only been upgraded, it has also been augmented by a series of symbiotic experiments that use the very technology and supporting infrastructure of the LHC to peer into the void beyond the standard model. Today, we will focus on one such symbiote, a new crowbar designed to feel for and gain leverage under the edges of the standard model. A mysterious box that now sits 70 meters above the existing ATLAS detector, staring down from on high. The first prototype components of an experiment known as ANUBIS. Could it be that the mythical Egyptian god of death will breathe life into the LHC's quest to uncover the tantalizing secrets buried beneath the expansive desert sands of our ignorance? The resilience of the standard model has inspired theorists and experimentalists to propose new methods by which signals of physics beyond the Standard Model could be created and identified. Many hypothetical extensions to the Standard Model that theorists have proposed to address the issues of dark matter, neutrino masses, the lack of antimatter in the universe, and other puzzling open questions in particle physics predict the existence of new, neutral particles with long lifetimes. Particles that travel tens of meters from the point they were produced before decaying. Long lifetimes and flight distances on the scale of typical collider experiments. Particles we have so far never observed. Identifying significant numbers of long-lived neutral particles at the LHC could therefore be a smoking gun for new physics. Particles, the ANUBIS experiment, is designed to stare into the void for. But why can't we simply look for such long-lived particles using the current LHC detectors? The enormous particle physics detectors at the LHC, such as ATLAS, a 10-metre tall monster of steel and silicon weighing more than 7,000 tonnes, may seem like relative behemoths, but they are simply too small to detect the decays of long-lived neutral particles. When the LHC smashes protons together at almost the speed of light in its detectors, the tremendous energy of these collisions can be used to generate the masses of new massive neutral particles, such as the now infamous Higgs boson, E equals mc squared. The highly energetic neutral particles produced spread out from the point of interaction, but many, like the Higgs, don't tend to live very long or travel very far from their point of creation before decaying, often into charged particles such as electrons or muons. These charged particles traverse layers of silicon pixels surrounding the interaction point and leave characteristic trails of ionization or pixel hits. These hits can be joined together by computer programs to reconstruct the flight paths of charged decay products and show that they originated from the same position in space and the decay of a heavier, neutral mother particle. Particles that are otherwise invisible and leave no tracks of charged ionization on their own. This is exactly the way in which particles like the Higgs boson and the Z boson were discovered, a process known as reconstruction. But what happens if a neutral particle doesn't decay before it punches through the layers of the ATLAS detector? There would be no charged particle decay products observed in the detector, and the eventual decay of the long-lived particle would go unseen. We would never know the neutral particle existed. Put simply, the grandstand experiments at the LHC are best equipped to search for neutral particles which decay rapidly following their creation, so-called prompt decays, not long-lived particles. The decay properties of extremely long-lived neutral particles can be constrained by looking at the particles we detect from incredibly far-off astrophysical objects. However, that leaves a currently poorly charted middle ground between the smallest scales and the most astronomical. A desert where the decays of moderately long-lived particles that punch through our detectors and decay within tens of meters are currently entirely missed. Strange new particles associated with entirely new exotic processes beyond our current observations and understanding. Is the new physics that we crave eluding us simply because it eludes the scale of our detectors and ambition? Are exotic Higgs decays, supersymmetry, axions, and other such wonders merely hidden in the antechambers of our experimental setups that are yet to see the light of day? It would be possible to observe these new, long-lived particles decaying if there were an additional, extended detector far away from the point where they are produced. But how far, and where is the optimal spot? The longer-lived particles predicted by many standard model extensions are predicted to travel tens of meters before decaying. To be safe, we could expand the ATLAS detector by tens of meters in 3 dimensions. But such an expansion would result in huge additional cost. In addition, the detector is currently constrained by the underground cavern in which it is housed. Large-scale civil engineering would lead to disruption of the current ATLAS physics program and dizzying, spiraling costs. But what if we could instead extend the ATLAS detector along one specific, constrained, narrow path without ever starting up even one boring machine or digger? It turns out that we can. The ATLAS experiment lies beneath an 18 meter in diameter, 56 meter long access shaft known as PX14. Cranes use the huge surface shaft to transport physics equipment from the surface into the ATLAS cavern deep underground. Physicists plan to essentially extend the ATLAS experiment up the access shaft by installing particle detection plates within it. Detector plates that would lie an appropriate distance from the interaction point of ATLAS to detect the decays of longer-lived neutral particles, and all using existing infrastructure. An essentially free King's Chamber for new, beyond standard model physics. The large projected area of the shaft, and the fact that the shaft sits directly above and in close proximity to the ATLAS detector, means that if they exist, many long-lived particles of particular masses produced in ATLAS collisions will pass through the tracking layers, even though the PX14 shaft represents only a small fraction of the solid angle around the ATLAS detector. This remarkably efficient, opportunistic, symbiotic detector extension has been dubbed ANUBIS, an underground, belayed, in-shaft search experiment. Current plans suggest that ANUBIS will consist of 4 tracking stations, evenly placed in the PX14 shaft, every 18.5 meters. Since PX14 is an active service shaft, the tracking stations will be lowered into the shaft by steel ropes and affixed to the shaft walls by mountaineering cams. The weight of the tracking stations themselves securing the stability of the planes as they dangle tens of meters above the cavern below. Such an approach allows ANUBIS to take physics while ATLAS is in operation, but also to be retracted rapidly when the service shaft is required, or in the case of an emergency. An elegant solution to a difficult logistical problem. Each tracking station will consist of 2 triple layers of resistive plate chambers. These act like 2-dimensional Geiger counters and detect the passage of charged particles through them with high efficiency, and high spatial and temporal accuracy. By joining together the hits in the rows of tracking stations, we should be able to trace the flight paths of charged particles traversing the PX-14 shaft and project combinations of them back to the same points in space within the shaft. In such a way, we may be able to precisely observe the decay of new, never-before-seen long-lived neutral particles currently missed by the existing ATLAS detector. The proposed ANUBIS setup is a beautiful solution to a very difficult logistical problem, an elegant setup to facilitate additional physics at minimum additional cost and while causing minimal disruption. However, it is the full integration of ANUBIS with ATLAS, the combination of Greek titan and Egyptian deity, that makes this proposed experimental setup incredibly powerful. When searching for new, not-before-seen neutral long-lived particles, it's possible that we can be deceived. Common, long-lived, neutral standard model particles, such as neutrons or K-long particles, which we are well aware of and familiar with, could be produced in an ATLAS collision, traverse the ATLAS detector, and decay within the shaft. If we are not careful, the decays of these background particles could be misidentified as the decays of novel, long-lived particles. Eliminating, or at least severely reducing such background decays is essential to the search success of ANUBIS and relies heavily on the already operational ATLAS detector. Firstly, ATLAS acts as a passive shield. ATLAS is a huge detector consisting of concentric rings of steel, silicon, and electronics. Most of the standard model particles produced by the detector never make it out of the detector and all the way up the PX-14 shaft, due to the sheer amount of material they need to penetrate. However, such shielding is not perfect. To identify and veto remaining unwanted background decays, ANUBIS must also use the ATLAS detector and its systems to provide active vetoes of candidate long-lived particle decays. Background standard model neutral particles like neutrons and K-longs are typically not produced in isolation by proton-proton collisions, but are regularly accompanied by high-energy jets of other particles. The ATLAS detector can detect and reconstruct such jets, allowing ANUBIS to demand that any candidate decay it observes be significantly displaced in angle from jets and tracks produced in the ATLAS detector. Less mischaracterizations, lower backgrounds. In order to reach the approximately background-free regime that ANUBIS demands, multiple such vetoes are required, and the new detector extension must therefore be fully integrated with the electronics and timing of its host detector. Of course, this mutually beneficial relationship is a two-way street. If ANUBIS is capable of identifying hints of new physics in proton collisions, ATLAS will be able to characterize additional particles that are created in these collisions and constrain the possible new physics models that are at play. The more information physicists have, the better. If the design and physics targets of ANUBIS can be realized, we will be able to probe new physics models that we have never been able to probe before, and set limits on theory that are tighter than any previously established. For specific beyond standard model physics scenarios, ANUBIS could improve the LHC sensitivity by 2 to 3 orders of magnitude at large decay lengths, compared to currently operating and approved future experiments. Simulations indicate that ANUBIS hits a sweet spot when searching for the decays of long-lived neutral particles. It is sensitive to decay times that are not too short, but not too long either. It is a Goldilocks of a physics experiment, just right for mapping the uncharted regions of our knowledge. For now, ANUBIS is in its pro-ANUBIS prototype stage, a 1 by 1 by 1 meter prototype tracking station module has been constructed and will be moved to various positions within the PX-14 shaft to measure the particle fluxes present during the current data-taking run of the LHC, and to study the prototype detector's performance, response, and radiation hardness in detail. The electronics of pro-ANUBIS can also be synchronized with those of Atlas to ensure that both can read out data related to the same individual proton-proton collisions. The ultimate goal is to correlate these measurements with expectations of particle fluxes calculated from detailed standard model simulations, and to evaluate whether ANUBIS in situ really will be subject to incredibly low, predictable, mitigatable backgrounds and capable of detecting new, long-lived neutral particles. As the LHC continues into a third decade of proton collisions, the thirst of CERN physicists to discover new and revolutionary subatomic physics remains undiminished. So much so that ANUBIS is not the only experiment looking to discover long-lived particles at the LHC, nor the only such experiment taking maximum advantage of the LHC's existing technology and infrastructure. The complementary phaser experiment is looking for lighter, long-lived particles 480 meters downstream of the Atlas detector in the LHC tunnel. Methuselah is a proposed large-scale surface detector above the CMS detector, while Codex B is a proposed detector to be installed in the LHCb cavern. Dedicated experiments for long-lived particles with exotic electromagnetic charges include Millikan, searching for milli-charged particles in the drainage gallery of CMS, and Modal, that is seeking to discover magnetic monopoles. In addition, the PX56 access shaft of the CMS detector and the PX16 secondary Atlas access shaft provide opportunities for alternative or additional experimental setups. LHC physicists are incredibly resourceful. As the LHC matures and continues to tackle the most pressing questions of fundamental science, this rich tapestry of complementary, symbiotic experiments will work in unison to probe as much of the parameter space of long-lived neutral particles as they possibly can. In Egyptian mythology, ANUBIS was the jackal-headed god of mummification. He was the god of the dead, and the escort of the newly deceased into renewal in the afterlife. Could the LHC's ANUBIS become a similar escort, resurrecting particles that would have previously passed beyond our analysis and observation, and finally allow us to reach the hallowed ground beyond the standard model? I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.